As educators, we must remember that we are also students. And as students, each and every one of us, I say to you this: I hear and I forget. I see and I remember. I do and I understand. And if we only had a computer, boy, the things that we could do together. Oh boy, oh boy, oh boy, oh boy.
And the things that are being done with computers. Apple Computer invites you to join us as we explore the exciting world of math and data analysis. It's a world that has come alive with visualization. Today we'll look at mathematics, statistics, and scientific visualization tools, and you'll see how these tools are revolutionizing both the classroom and the research lab.
Hello again and welcome. While we were having a little fun with the opening of today's show, there is a message there. A message I not only believe, I know to be true for me. Tell me, and I will forget. If I see something, I can learn it. If I'm able to do, only then can I really understand. You know, my chemistry professor would use a simple object like this to help me see things that a textbook or a photograph just couldn't provide. While that helped, it still wasn't quite enough for me. But what if I could have taken this object and changed it, rotated it, manipulated it in some way, perhaps even to correspond to other data? While it's somewhat hard to do here and impossible to do in a textbook, a lot of schools are discovering how a computer, with the aid of visualization tools, can bring math and data analysis to life. Today's program is very exciting for me because I learn by doing. And this show introduces some tools that not only bring data to life, but make it accessible to students. To get us going, here's Carrie Tengler, Marketing Manager for Higher Education, with a tie that just won't quit. Carrie?
Thanks, Bert. Well, we do have lots to show you today. You'll see examples of things that you can begin doing tomorrow in your classroom, and some exciting things that are still in development, but not too far out of reach. Joining us here today are Wade Ellis, math instructor at West Valley College in Saratoga, California; Paul Velleman, an associate professor of economic and social statistics at the New York State School of Industrial and Labor Relations at Cornell University; and Rob Wolf from Apple's Advanced Technology Group. Each of them is armed with several exciting demos. And as always, at the end of today's program, we'll save some time for Q&A. Here are the numbers. For those of you outside California, call 1-800-344-0348. Inside the state, you can call 408-974-4400. If we don't get to your question on the air, we're going to stick around for another 30 minutes after the show to take some additional questions. Remember, we may be off the air, but our phone lines will stay open for an additional 30 minutes. All right, let's get going. This is West Valley College in Saratoga, California.
This is very, very important. Now, it's not very, very important because it's great and difficult mathematics. It's very important because you're going to do it a lot in this course. Editing features of the
And this is a look at our first guest at work in his classroom. Wade Ellis teaches math, and the class you're seeing is his introductory calculus class for business majors. One of Wade's favorite, and I think he'll say most used tools in this class, is a software package called Maple.
But these are a little bit better graphs, and they have a feature that's wonderful.
Well, Wade, before we get into Maple, let's talk a little bit. Maybe you can give us a little bit of history on how you began using the computer in your class and when you actually started.
I started using computers in mathematics classes 10 or 15 years ago. At first it was just trying to see what we could do with the tremendous computational power that computers had. Later on, things changed.
Great. Why then Maple? There are several other packages, both for the PC and the Macintosh. Why did you select Maple as the computer algebra package?
Well, Maple was the first package that was available for the Macintosh, and we had a Macintosh laboratory. It was a natural match, and also Maple was the first of the computer symbolic algebra packages that were available on small machines that I thought was appropriately put together for our students. It needed to be user-friendly. It needed to be possible for students to understand how to input information and to understand the output. Maple fit the bill in these regards.
Great. Well, maybe you can give us an example of how you use it in the classroom.
Well, let's start with the following problem about box office receipts for a movie. As you can see, this gives rise to a function. This function can be entered into Maple. So let's look here. This is what a student would type in. There's some syntax that you have to worry about. It doesn't look exactly like what was in the textbook. If we actually do enter it, however, the student can see that what they entered, is exactly, well, it too doesn't look exactly like that, but they can certainly tell that this is the correct function.
It's actually closer to what they'd see in a math book.
Exactly. So once we have it in, we can do things with it, and the standard kind of thing to do with this in an attempt to analyze the function is to differentiate this function with respect to x, and you'll notice there are parentheses and semicolons and that sort of thing, some syntax. Now, the result is not all that complicated, but for my students in a business calculus course, this is difficult to simplify. And they can't really use it in the form that it first shows up, both when they differentiate it with paper and pencil techniques and as it appears here. But we can use the computer to simplify this. The quote marks indicate that I'm going to be using the last thing that was printed out, the last thing in time, the semicolon at the end. And now it simplifies this original, not so complicated expression into something that's much tighter. And my students can see, for instance, here that if x is positive, the denominator is positive, the numerator is positive, the whole thing's positive. They know enough about the first derivative, which we have here, to say, well, gee, the function ought to be increasing, which is a nice fact about total receipts. They should increase over time. Now, once we've gone that far, we might want to say, gee, what happens when to this particular function, as x gets large, approaches infinity, and this is the way you would write a standard kind of idea that's available in our course. What's the limit as x goes to infinity? Here, we come up with an answer. It's 120, so you can get both symbolic kinds of answers and numerical kinds of answers with Maple and other computer algebra systems. Well, at that point, we have gone through a number of symbol manipulation kinds of things. Students have some idea of what might be going on with the function from using the mathematical tools with the help of Maple, pardon me. And now, what else could we do?
Well, that sort of gives us a number, but is that really the end of this problem? What about, given that the theme of the show is actually visualization, what about some of the graphics that are capable? Does that provide any additional insight?
Yes, it does, and Maple allows us to do that sort of thing. We can plot this particular total receipts expression or function as x goes from, say, 0 to maybe 25. Now, I've chosen these numbers so that the graph looks reasonable. My students might graph it several times. So we start off the process of plotting this particular function using Maple.
This would be a good time to mention, I think, that we're running Maple, which is a fairly powerful computer algebra package, on a 2 meg Mac Classic. So even robust packages like this can be run in a relatively low-end machine.
Indeed. And that's an important consideration when you have lots of students that you'd like to service, and as we do at community colleges, we don't have a tremendous amount of financial resources. Well, here's the function, graphed. Now, we can sort of see some of the things that we saw numerically. It certainly, and symbolically earlier, the function does indeed increase, as you can see with the little crosshairs. Starting over here, it starts at 0 and increases. It flattens out here for a while, and apparently if we went beyond 25 years, it would flatten out some more. Well, can we tell exactly how far it flattens out? Well, sure. It's 125 here. It's below that, and we already know from the numerical computations that it would be at 120, that it wouldn't quite get there, but we would have total receipts that we would be at most $120 million. This is, in the past, about where we stopped with this problem. Mm-hmm. You get the graph, you can say some particular number, it's 120, and that would be what would be the answer given by students. Now we can go beyond this because students are still, they still have some energy left for this problem. They can go forward on this, and you can start asking questions like, well, suppose a videotape company came in and made an offer of $5 million after, say, 12 years. Is that a reasonable, after 12 years, they're going to offer $5 million for the rest of the rights, for rights indefinitely from there on? Could you analyze that particular offer? Is it a good offer, a bad offer, a great offer? Should you take it right now so that they can't talk to their lawyers about it or make an additional analysis? That's the sort of thing that we can do now. We can also look at the fact that it's increasing very rapidly at first, and then it starts to level out. And where does it start to level out? Where's a good point to start talking to the video?
Right.
Yeah, exactly.
So by getting the students away from the actual manipulation and allowing them more time to work with what used to be the answer, they can actually develop further insight into the problem.
That's our hope, and that the technology will give us access to ideas that the students might not have had as much opportunity to look at, or in some cases, any opportunity at all to look at. So the technology gives us access to ideas.
Great. Well, we mentioned earlier that there were several other packages available on the Macintosh. Maybe you could take a minute and go over some of those and call out some of the strengths of the other packages.
Well, there are a number of other packages on the Macintosh and on other platforms. Particularly, the ones that I'm relatively familiar with are Maple, Theorist, and Mathematica. They all have the three standard characteristics in that they do numerical, graphic, and symbolic computation. Maple is strong in symbolics and numerics. It runs on multiple operating systems, so that you don't have to just run it on a Macintosh, but there are other places that it runs as well. And it runs on 1 megabyte of memory. Theorist, it has a very strong Macintosh-like user interface where the things that are displayed on the screen look very, very much like they do in a typeset book. It has excellent graphics, both 2- and 3-dimensional graphics, and it also runs on a 1 megabyte system. Mathematica has, as all of them do, symbolics, numerics, and graphics processing, and it possesses a unique notebook and front-end capability. The front-end capability allows you to access the computational power from your own machine at some other site. And that's a very powerful kind of thing as well. The notebooks are used to present mathematical information in a new and interesting way. And finally, the programming language in Mathematica is very, very flexible.
Great. Well, Wade, we've seen a little bit about how you use Maple in the classroom in the opening video clip, but maybe you could tell us a little bit more about how it's actually being used in your classroom.
At West Valley College, we use the computer to supplement a traditional business calculus course. It's an enhancement. I also use the computer as a projection device. In that way, I can, in class, actually go through many more examples than I could with paper and pencil kinds of activities or chalkboard activities, and the drawings that come up are much more accurate. At the University of Illinois, however, they've taken it all a step further.
Right. What you're about to see is a calculus course taught by Jerry Ewell and Horacio Porta at the University of Illinois. They hold 1 lecture per week, and the rest of the students' time is actually spent in the computer lab. They've replaced the traditional calculus textbook with a series of Mathematica notebooks. Here's a look.
We always realized that the old-fashioned course amounted to us reciting a catechism to the students, which they asked them to repeat back to us. And we realized we became curators of the dogma and arbiters of truth, and we were not teaching mathematics, we were teaching religion.
How many expansion terms did you make it out of?
Well, no, I don't think it does. Let's see what they asked for here.
In this class, the focus is now switched onto the student rather than the teacher, and I think that really makes a difference with their confidence, because once the student starts learning on their own, they're teaching themselves rather than being taught to. They get more confidence and they're able to learn faster, and their creativity starts to come out more.
It's kind of a self-study thing, self-centered. I meet with them in the class one day a week and then give a quiz another day, and then the third day we're just in here. And when I'm in here, I help them a little bit, but mostly I have them do it on their own.
It's hard to answer why we started. Once you start this,
There's a little bit of craziness involved.
There's a little bit of craziness, yes, sure. But once you start this, the students convince you that you're doing the right thing, and you keep on doing it.
I really feel that I'm learning more through the computer because I think I'm a visual learner, and it's much easier for me to learn from plots. I mean, because this has the capability of doing three-dimensional plots as well as just two-dimensional. It's easier for me to see, to understand what I'm learning because I have that visual reference there.
You might not be able to integrate as quickly or readily as someone in another Math 242 class, but you'll gain an understanding that they can't really gain, since you'll see like visual and graphical representations of what formulas you're trying to use.
We now have students who have identical ACT scores as the general population of blacks and Hispanics that were doing very poorly. They're getting 75% A's and B's. That's compared to the overall general population that's getting 45% A's and B's.
Out of high school, I got a position with a construction firm, and I enjoyed doing that kind of labor work and building and stuff, but that went down the tubes, so I got a janitor job here to tide me over. Found out that I had full tuition waiver. I had never touched a computer until I took this Mathematica-based calculus, and just got into it.
When you do hand computations, you always have limits. You have limits with cumbersome mathematics. If it takes a long time, you're going to make silly arithmetic errors. But with the computer, you have very, very few limits anymore.
Well, teaching a regular course is such a boring activity. I wouldn't be able to do that ever again. I die of boredom.
But we actually have students who have a view of mathematics that in some ways is more mature and more realistic than some of our graduate students have, mainly because they've seen for themselves.
How about our colleagues, too?
Some of our colleagues, yeah.
Well, Wade, I thought there were a couple of interesting things in that video. The first is that having a lab set up like that really takes Professors Yule and Porta in particular out of the role of being a presenter and puts them in a role of being a coach. We saw Jerry with a couple of students basically working with them as they were working through problems on the computer. Another thing I thought was very interesting is the students seemed very interested in the class, which is not my recollection of calculus. How has the use of computers in your classroom been accepted by the students?
Well, the class I use is a business calculus course that occurs at 7:30 in the morning, and the students are not that eager to be there, and when they get there, they're a little drowsy, and with the standard paper and pencil kinds of things, they're not balls of fire. But given a little encouragement, they come alive mostly, and it's very important to use the computer because this gets even more energy out of them, and I do see the same kind of thing that Yule and Porter see, that people become excited, they become excited about questions that are involved, they ask me, they ask each other, it becomes a much more interesting educational environment in which they can learn.
Well, you're a brave man to teach a business calculus class at 7:30 in the morning. I know one of the questions I'd have if I were in the audience is just how much does it cost to set up a situation like this? At Illinois, we saw probably 35 Mac 2s, and you had a reasonably nice setup at West Valley College as well.
At West Valley College, with the help of an NSF grant, 3 years ago, the machinery you saw there cost us about $100,000. You could do the same sort of thing now for perhaps a third of that, somewhere between $25,000 and $35,000.
Great. Well, Wade, thanks very much for joining us. Wade will be back with us a little bit later for the Q&A. So far, we've seen the application of some fairly abstract concepts. Let's turn to something even more applied, the science of statistics. That's a cold scene. This is Ithaca, New York, and this is centrally isolated Cornell University. Our next guest, Paul Velleman, has successfully integrated technology into his introductory statistics course. Here's a look at Paul at work, and he's using a software package that he developed called DataDesk. We'll see and hear more about that in a bit.
We'll be doing a lot of that, and again, we'll be using the computer a lot to do that. Now, the idea of having a distribution of numbers is usually depicted with some sort of a shape. The idea is that the largest value, the smallest value, and we take the middle point between them. So we have some data here. The histogram is going to appear on the screen like this. Now, this histogram is a little bit confusing. Here are all the heights.
A main benefit would be learning the concepts of statistics, whereas some professors just want you to learn the mathematics behind everything. Like, you know how to calculate it, but you don't know why you're calculating it, and you don't know what the effects are and what the consequences are. And with DataDesk, you learn the consequences, and you learn statistics as a discipline instead of just as, like, you know, just doing numbers.
And now if I let go of the mouse, you'll see the histogram will redraw with fewer bars. And in this case, that makes things clearer. Again, I get exactly the same plot, only now what do the axes say? Instead of 58, 68, 78, it says 580, 680, 780.
Professor Velleman uses the computer to demonstrate and show you all these complicated looking details of the programs, and you can then go, and it's remarkably easy to use, and you can do these same things, and there's no distance between you and the teacher.
So we'd summarize with a typical value, some value that talks about the middle of the distribution, some central value.
Well, Paul, most students don't usually like statistics, and yet yours seem very interested and very alert. What gives here?
Well, Carrie, we find that if we put the students on the Mac right from the start, that empowers them. From day one, they're analyzing data, they're seeing patterns in the data, they get some sense of why we're studying statistics in the first place. They get comfortable on the machine, and later on in the course, when we start using the computer to help them understand abstract concepts, they have a basis to work with.
Well, maybe you can take a minute and tell us a little bit about how your class is structured.
Well, there are several ways you can do a class like this. A lot of colleges license a laboratory facility, and students work there. At Cornell, what we've done is we have every student own his own copy of the student version of DataDesk. That way, they can work on any machine. They can work in our lab, they can work in their dorm rooms or in the fraternities, wherever they might find a computer. And we find that that's worked very well for us.
I can imagine. I remember some painful evenings waiting in line for a terminal to open up in the basement of some computer building. I also seem to remember spending a good 15 minutes at the beginning of each class period learning the particular computer commands for whatever statistical technique we were working on at that time. Is that still the case?
Well, that was actually one of the reasons we moved to the Macintosh. We figure that we've gained about 2 lectures in the course of a term that we previously had to spend introducing students to how to log onto the machine and how to use each command on the program we were using. These days, we offer our students a single introductory lecture on the Macintosh if they need it. And thereafter, they're pretty much on their own. They see the package used in class, and they have weekly assignments. But we don't have to give them any additional instruction. One reason for that is that the desktop that we have in DataDesk resembles very much the desktop they see in the Finder. Let me show you.
Great.
This desktop here is the DataDesk desktop. The icons represent variables in our data set. So here we have data on cars from Consumers Union.
This is actually real data.
This is real data. This is a data set that I would use in class. We always work with real data once we're on the computer. It's a data set that I use in class and that we use for exercises sometimes. We have the name of the car, the country of origin, the gas mileage, the weight, and so on. And you can open up the icons and see inside that the data is right there. So we can see that the Chevy Caprice Classic is made in the United States. It gets 17 miles to the gallon and weighs about 3,800 pounds. But the nice thing about this interface is that we can close these up because statistics really isn't about numbers.
What do you mean it's not about numbers?
Well, that's something we have to teach our students too. Students get very involved in getting the right answer, and using the computer, they can trust the computer to do the calculating for them. Really what you do in statistics is you try to relate concepts. So, for example, here we might be interested in how gas mileage relates to weight. We would start to look at that by drawing a plot. So we might make a scatter plot of gas mileage against weight. And when we open up that plot, you can see that there's the sort of pattern you'd expect. There's a decreasing pattern here that heavy cars down here, cars weighing 3,000 pounds or more, are getting the worst gas mileage, less than 20 miles per gallon.
As you would expect.
As you'd expect. And up at this end, cars down under 2,000 pounds are getting gas mileage up in the 30s. So they can start by understanding that sort of pattern. They can go beyond that, though, because if they pick up a tool like the question mark tool here, they can start identifying individual cars. For example, this car, the heaviest car in our data set, is a Buick Estate station wagon. Or we could look at another car here. This is the Ford LTD. So you can see that these are big cars. And if we come over here, we have a Dodge Omni or a Datsun 210. You can see that these are the little cars, and that helps the students to get a little bit more oriented. We can even go further, introducing additional information. We have, for example, the variable that is country of origin, and that's just, those are words, so we would make a bar chart. And we've coded those according to whether the car is manufactured in Europe, Japan, or the United States. What's really powerful is to be able to look at these two plots together. So we could, for example, take the knife tool and slice across the scatter plot, selecting cases as we go, and you can see the bar chart filling up as well. So that here we have the cars that get the worst gas mileage, and pretty much as you might expect, most of them come from the United States.
As we've come to expect.
That, however, raises some interesting questions as to why that might be the case. We could, for example, click on the U.S. bar and notice where the U.S. cars are in the plot. Let's give them a different color and a different symbol. And now you can see a very interesting pattern in this plot. Not just at the high end where the cars are very heavy and get low gas mileage, but all the way along this plot, the U.S. cars seem to lie along the top of the plot. So even in mid-range, U.S. cars get better gas mileage for their weight than other cars of that weight made elsewhere.
Which is not at all what we've come to expect.
Which is not what you come to expect. We could add a regression line, and you can see the U.S. cars generally are falling above the regression line, and the non-U.S. cars are often falling below the regression line. Well, by playing with patterns like this, we get the students to think about the data. That draws them into it more. They get a sense of understanding what's going on because they can interpret it. They can draw conclusions from it. We've also snuck something else in on them here. They're working with 3 variables. They're doing a multivariate analysis very early in the course. Now, later in the course, we'll come back to doing multivariate things, but it won't be a new concept to them.
Well, now you've shown us something that's kind of sneaky and also very interesting, but so far it's been pretty much straightforward. What about when you get into some of the abstract concepts that you mentioned before, like inference and correlation?
Well, we can use the computer as a laboratory. The computer can generate random numbers, and we can use those so students get a chance to work with abstract concepts and visualize them. Let me give you an example here. I've generated numbers for x that just run from 1 to 100. Then I've generated random normal error and added it to x in an amount controlled by this slider here. In this case, it's 0. And I've also computed the correlation of x and the y variable here. And you can see the correlation is 1, and we have a linear trend. If I grab the parameter, however, and push it, I'm adding more and more error to the data. Here I have a correlation of 95%, and you can get a sense of what 95% looks like in the plot. I can push it a little further, and you can get, here's 80%. So you can get a sense of how correlation actually looks. That's something I'm always asked whenever I teach correlation is, well, what does 80% correlation mean? And one good way to show that is to just give students the chance to slide it back and forth for themselves and see what the relationship looks like.
So in addition to using it with real data, you can also use it as sort of a simulation engine.
Absolutely. It's a very effective way for students to work with these abstract concepts.
Now, Paul, another thing I've noticed as you've been going through this is that the student or the instructor could actually interact with the data very easily by using the question mark tool or the knife tool. Is that also an important concept in your class?
Oh, very much. When students work directly with the data, when they touch it and manipulate it, it's a much more immediate experience for them. So they're much more involved.
Great. So far you've shown us a lot of things that really apply very well in the classroom, but I know that statistics are used across the campus in both teaching and also in laboratories. What are some examples of how you could use a tool like this in those situations?
Well, DataDesk is based on an exploratory data analysis model, which is heavily graphical, looks at the data, trying to find patterns in the data. That kind of approach has entered the scientific laboratory and the social science analysis hand in hand with more traditional methods. And DataDesk works very well to do that and works very well with other programs. Let me give you some idea of that. Here we have the same plot we looked at before, gas mileage against weight, but I've added an additional variable. I've thrown drive ratio into the model, and I can now rotate that and visualize the 3-dimensional relationship. Now, in this particular case, one of the things I can see is that this is a flat surface. You can see there it is on edge, and here it is face on, and that tells me, for example, that a regression analysis might be appropriate for these data. So I could go up to the variables and say I wanted to predict gas mileage from weight and drive ratio in a regression, and compute the regression right there. Now, that would be a typical way to start an analysis of these data. But we can go beyond that because no one package is going to do everything that any scientist or social scientist wants to analyze his data. And one of the really nice things on the Macintosh is it's very easy to move data among programs. So, for example, I could grab these variables and I could...
So sort of cut, copying, and pasting.
I could grab these variables and copy them. I have to make sure I've grabbed them if I'm going to do that. And simply move to another program. Now, I had launched Systat here, which is one of the most powerful of the statistics packages on the Mac. Systat has all the kinds of techniques you'd find on a standard mainframe statistics package, and you have that ability directly on your Mac, and it's this easy to pick up your data and move it there and have all of that power available to you.
That's great. So in essence, you can sort of pick your tools in cafeteria style.
Absolutely.
Great.
It's a very effective way to work.
Wonderful. Well, thank you very much, Paul. Again, Paul will be back with us a little bit later for the question and answer period. We're going to go through the phone numbers one more time. For those of you outside California, that's 1-800-344-0348. Inside California, you should call 408-974-4400. Well, we've all heard the expression that a picture is worth 1,000 words, and Paul has just shown us that with DataDesk. But what if you had 250 megabytes of image and terrain data? Then what? You might get something like this. This is a very small portion of the Mars Navigator, created by Apple Computer's Advanced Technology Group. Our next guest, Rob Wolf, is a part of ATG and was project leader for the Mars Navigator.
Pavonis Mons. Noctis labyrinthus. Valles marinaris.
Rob is an astrophysicist who came to Apple 3 years ago from NASA's Jet Propulsion Laboratory to lead Apple's scientific computing effort. Rob, can you tell us about what we were just looking at?
Well, the Mars Navigator project was produced as part of Apple's exhibit at the Silicon Valley Technology Center in San Jose. The Mars Navigator project wasn't one of these really snappy projects that was easy to produce. It took 2.5 years, during which time we pushed technologies in computer graphics, laserdisc technologies, audio and video, producing over 10,000 frames, over several thousand hours of computer rendering time, and 30 gigabytes of data, which we then mapped into a dual laserdisc system, which is controlled by the user with a supercard front end. These kinds of images you've seen with terrain images and footage of the Gulf War. This is the kind of technology that we're working to bring to the desktop so that students and teachers can use it in their daily work.
Great. Well, in addition to this imaging and terrain mapping, what other kind of things are you working on in ATG?
Well, ATG's efforts in scientific computing basically is sort of a three-pronged approach. First, we work with users to define needs and develop prototypes. Then we also work very hard in ATG to develop our own technologies, both as part of the scientific computing effort and as there are many general technologies being developed in ATG per se. And finally, we work with selected third-party companies like Spyglass and Electric Image to help develop new products for the marketplace.
Well, how about you show us some of the things you can do on a Macintosh right now?
That sounds like a neat idea, Carrie. Well, hey, we have a Mac here. And what I have on the screen here is an image from the same data set from Mars Navigator this is an image of Arceus Mons, one of the shield volcanoes on Mars. Now, this is an electric image. And what I'm going to do is actually what we've done here is take this image, and it's been mapped onto the corresponding digital terrain data here. Okay, so you can see the actual three-dimensional structure. Mike Backus and I then took this data in an afternoon and created an animation where we, about 2.5, 3 hours on a Mac 2 CI, we actually are flying around the volcano itself here.
Now,
okay?
Is it noteworthy that you did it in 2.5 hours?
There are two things noteworthy. First, that we did it in 2.5 hours, but secondly, until less than a year ago, you had to go to a very high-end mini supercomputer with very expensive software with an expert, okay, without a Macintosh front end to it. And you had to have the expert sitting there, and you'd spend quite a bit of time doing this kind of rendering. The fact you can do it on a Macintosh today is sort of a vision that a number of us had a number of years ago. In fact, a friend of mine, Dave Pieri, a planetary geologist at JPL, saw this animation on my computer one day, and he sort of had a religious experience, started jumping up and down, spouting geology words. He discovered something here, which I think he's writing a paper on.
Great. Well, what about what you've shown us so far is basically static images with the terrain mapping, but what about dynamics when you get into, you know, what would happen if that volcano had to spew something?
Well, as my hand is on the mouse here, what I'm going to do now is something that Mike Backus did for me just the other day as I was getting ready to come up here for the show. What this is some new technology developed by Electric Image very recently that allows us to actually do particle simulations, okay? And we have volcano stuff, like spewing up out of the sky, billions and billions of little particles running around your favorite volcano. What this isn't exactly a volcanic simulation, but this technology will allow teachers, students, and researchers to simulate everything from volcanic plumes to various kinds of fluid phenomena. So this is very critical technology, and to have this on the desktop today is really remarkable.
Great. So what you've shown us so far are a couple of astrophysical examples. Are there applications of this technology in other areas?
Well, what we found over the years, if you look at the history of scientific computing, is that scientific computing is generally the forerunner of computing technologies that then move out into the general marketplace. And basically any discipline that uses data can make use of these visualization technologies. That includes obviously things like molecular modeling, but in ways that you normally don't think of. You have econometrics, stock price analysis, and of course weather forecasting, the kind of thing that you see on the news every night.
Well, in addition to ATG, is there anybody else who's working to apply these technologies across these various curriculums that you've just mentioned?
There are a lot of people now in the last few years who have begun to work with visualization technologies, but perhaps the leader, and I guess we have a very strong partnership with them, is the National Center for Supercomputing Applications in Champaign-Urbana, Illinois. These folks at NCSA, they faced a challenge as part of their charter from the National Science Foundation of integrating the entire computing environment, from supercomputing down to the desktop. The application domains that NCSA deals with initially were principally scientific research for high-end scientific computing, but now are migrating to education and business computing. We realize, both at Apple and of course NCSA, we realize the Macintosh cannot and really should not need to do everything, because the real-world computing environment is distributed, many different kinds of systems. What we need to do is to balance the load. So let's hear from Mike Norman and Joe Harden at NCSA, who are going to describe a bit of their work.
NCSA is one of 4 supercomputing centers funded by the National Science Foundation. Here in the Beckman Institute, NCSA works to provide researchers access to advanced computing hardware and software, the most advanced available at any given time. Over the years, this key notion of access has changed and diversified considerably. In the beginning, access meant access to our supercomputers over national networks. Then it meant access to scientific data produced by these researchers. And there, NCSA took a key early lead in developing scientific visualization software for desktop workstations, in particular the Macintosh. Recently, we've discovered that these tools, developed for researchers, are excellent educational tools, providing students in the classroom access to new ideas and insights that would otherwise be difficult to achieve. Who are our users? Our users are over 2,000 scientists and students in over 200 affiliate universities, working in disciplines as diverse as agronomy to astrophysics, as diverse as botany to biochemistry.
The Software Tools Group at NCSA has the job of trying to bring as much power to the individual on their desk as possible. When you look at the National Center for Supercomputing Applications, supercomputing is in the name, but really the center's task is to try and facilitate scientific research as much as possible. That means that high-performance computing of all different types is a central aspect of the work that we do. For us, that means that the Macintosh, or a workstation that is approachable for individuals, not for people that have had years of learning in computer science or years of education in computer science, is crucial to getting the work done. And in the end, the most important thing is, how much work have you got done? Have you been able to push the envelope a little bit further? Have you been able to learn something new in the last few days, or in the last week, or the last month?
Well, Rob, one of the results of working with NCSA over the past 3 years is the migration of a lot of this technology from the research lab into the educational domain, as I understand it.
In ATG and throughout APA, we feel very strongly that tools that researchers have should be available to students. And so we're working very closely with the NCSA to help develop solutions to real-world scientific problems that then translate down to the educational domain.
Great. And here's Nora Sabelli from NCSA to help us take a look at that.
To take some of the tools that we have developed, like image and so on, that have proven extremely valuable to researchers in helping them manipulate interactively their data and understand more complex concepts that way, adapting them to use by students to precisely manipulate complex concepts and learn the same way that they will be working once they become professionals. The more you can deal with real-life examples, the better it is for students. Very often the examples in chemistry are sort of small and made up. The students don't really have a deep understanding of those issues, and we all know that you learn by doing, you don't learn by listening. The concepts that I mentioned are all very abstract, and we have to make them more concrete for students to be able to manipulate them and eventually understand them.
In addition to the chemistry project Nora just mentioned, NCSA is also developing a number of interactive visualization tools for computational fluid dynamics. CFD is a subject studied by literally every engineering student. It's computationally intensive, in fact, much more than you would typically run on a Macintosh.
Examples might be the way water flows through an irrigation canal, the way tea flows through the neck of a tea kettle, or the way air flows over the wing of an airplane. Kim Stevenson has been working on this project, and we can see here Kim setting up the initial conditions for a simulation that she's going to run on the Cray. This particular geometry or input deck for the simulation program is very close to being set up now. We can see that there are some obstacles inside of the geometry that are going to have some effect on the flow of fluids through this geometry. She's just defined the areas where the fluids will be coming in and going out, and I think at this point she is almost ready to run the remote simulation. In order to do this, all she has to do is select one menu item, and the simulation is then launched on the remote computer and fed the input deck. And there are results. Here we see Kim using the fiddle tool to compress the range of available colors to represent a narrower range of data values. We can see the banding effect in the image, and it's also apparent at this point how this can improve the scientist's understanding of the data set.
Although what Tom Rebin was showing was an example of computational fluid dynamics, these kinds of visualization tools can be used in any environment where you run computationally intensive tasks on a remote computer and you do your visualization and analysis on your Mac. The CFD demo that you just saw, for example, was basically done in real time. But a lot of times you may want to build a more complex visualization. So this next video, done by the visualization group at NCSA, is a visualization of smog over LA. What you're seeing here, all those little balls represent tons of various kinds of pollutants, okay, being driven by the wind. The wind is represented by the various arrows. And you can see, as time progresses, how the smog moves over to San Bernardino. Anybody out there from San Bernardino, don't take a breath over here. This is also good to show during Super Bowl. Now, when people think that it's nice to move out to LA. This visualization took several months to produce by the visualization group at NCSA. But our objective with NCSA here is to migrate these tools to the desktop environment.
So Rob, now we've gone from the two-dimensional domain with the CFD type tools into the three-dimensional domain with the smog video. What about volumetric data analysis on the Macintosh? Is that possible yet?
That's a very interesting question, and Carrie is a wonderful straight man for this, because I happen to have on the screen here a tool called Dicer, which is produced by Spyglass Incorporated. And what Dicer does, it's the first time that on a Macintosh you can do volumetric visualization. So what I'm going to do right now is to put some data up here from a computational fluid dynamics simulation done by Mike Norman. This is basically a gas jet, okay? And I'm going to slice this a couple of different ways here. What this does is it gives you a view into the interior of the data set, okay?
So, unlike the Mars mapping, which was essentially rendering the exterior, the surface, this is actually kind of an internal rendering.
That's right. What you have a lot of times in real data situations, okay, is that you have a parameter that's a function of x, y, and z. Now, if you simply do a line plot or some scatter plot or something like that, you can't get any idea of what that structure is. You have to really go into the data, and this Dicer is the first tool on a personal computer that allows you to do that. Prior to Dicer, you again had to go to very high-end systems, spend a lot of money, and have an expert hanging around working with you.
The wavefront PhD, so to speak.
The wavefront PhD, exactly.
What other types of technologies are you working on in ATG right now?
Well, what you've seen so far are technologies that exist today. In addition to working on technology integration with groups like NCSA and Spyglass and Electric Image, ATG, as I said before, develops its own critical core technologies in a variety of areas.
What do you mean by critical core technologies?
A wonderful lead into the Sinus Workbench project. ATG works on lots of things. One of our projects is called Sinus Workbench, which is the environment within ATG that a variety of technologies are developed within the domain of scientific computing. By using the Sinus Workbench to push technologies for researchers, we learn which capabilities need to be built into future Apple products for more general computing environments. These technologies eventually will migrate into areas like business education, or business education, the humanities and social sciences. One quick example here is the distributed computing technology, which allows the scientists to work with many different data and compute resources. This is the same technology that's known in the business world as complex systems. This enables, for example, a financial analyst to work with financial data sources or a travel agent to work with a travel reservation system.
Great. Well, Rob, thanks very much for joining us today. You've shown us some pretty interesting and I think very intriguing demos, and I'm sure it's going to generate a few telephone calls, which is a perfect lead-in for my next thought here. We're ready to go to the question and answer portion of today's broadcast. Once again, our phone numbers for those of you outside California are 1-800-344-0348. For those of you inside California, call 408-974-4400. If we don't get to your question on the air, we'll still be around for 30 minutes after the show to answer the rest of the questions. We have a question from Larry at NCSA. Larry? How you doing, Larry?
Can you hear me?
I can. Yes, can you hear me?
Can you hear me?
Yes. Larry, I can hear you. Go ahead. Larry, it sounds like we're having some video or some audio problems.
They can hear me? Okay, fine.
Gotcha.
The question is, how do we get software vendors who have traditionally been making their packages for standalone on the Mac to put the hooks in we need to use them as distributed packages over the national network? Because with the kind of powerful supercomputers that are on the national network, those can be just pulled into your Mac as if they were inside it on your desktop anywhere in the country. And yet most commercial software don't allow for that. What can Apple do to encourage that in future software products from third-party vendors?
Larry, I'm going to turn this one over to Rob and let him answer that. I think he's probably got a pretty good answer, and Paul probably has some thoughts on that as well.
From Apple's perspective, real quickly, I think that this is a new area that we're moving into. There's already been some work done on that in just the simple kinds of everything from Mac Workstation to the Oracle database products. But right now, by taking the lead from places like NCSA, we can begin to show our software developers through our evangelism program, for example, that there is more to life than just developing on the single Macintosh. Paul probably has some comments from a developer's perspective.
Well, I think that's right. One of the things that is clearly going to be very important in the future is getting data from a variety of sources. But when you get data that way, you have to worry about how to deal with that, because we haven't traditionally been designing packages even from the core out. So it's not as simple as just hooking in some communication hooks. You really have to rethink how you're going to deal with data that comes in that way. But it is absolutely the way things are going, and it's going to be a very important direction.
Great. How does that Is that a pretty good answer, Larry?
Good answer.
Okay. We have another call from Cal at Southern Miss. Cal, can you hear?
Yes, sir. Thank you. This question goes specifically to anyone with any information on this. This is a new program called HiQ by Millennium, and I'm wondering and wanting to mention to everyone to keep an eye out for it. I saw it in the February '91 Macworld. I wonder if any of you have seen this program or worked with it.
I've heard of it. Whoa.
Thanks, Rob.
Are you still alive over there, Cal and Miss? Ole Miss there?
Thank you.
I've heard of the program, and in fact, I mean to get down to see that. I think they're actually local, and I've been meaning to try and see those. I heard it's a very exciting program. So thank you for reminding me again. I'll put that on my calendar to go do.
I think if anybody does have any information on that, please call in and we can probably get your comments on the air.
Why not?
We have another call from Louise from the University of Minnesota for Paul.
Yes. I was wondering, Paul, if you could elaborate a little bit more on the concept of exploratory data.
Oh, my favorite topic. Exploratory data analysis really is a philosophy. It's not just a couple of plots or some new ways to look at data. It's an attitude that you approach the data with an idea of looking for patterns in the data rather than with an ultimate aim of just doing a hypothesis test. And as a result, you learn about the data from the process of looking at it. You're going to hear a lot about exploratory data analysis. It's really coming into its own because it's a very effective philosophy for looking at data that does not come from a traditional experiment. If you perform a designed experiment or a carefully designed sample survey, you probably want to use one of the traditional methods. But if you just have data in a database or in a spreadsheet or that came to you out of a government publication, an exploratory analysis can really be a much more appropriate way to look at the data. And with microcomputers and the graphics we have available to us, it's becoming a much more practical thing to do.
Great.
Louise, is that good enough answer?
Great. Thank you very much.
Good deal.
Thank you.
We have a question from Wade, from Wade, from Tom, for Wade. Tom is from Michigan Tech. Tom, go ahead.
Hi, Wade.
Hi.
Yeah, I have a question. Do you think that when you sit there and you leave a lot of the computation and the calculus up to the computer, that you kind of are denying the student kind of learning the task properly? I mean, I know it's a great tool for doing the analysis on it, but do you think that you maybe lose something when you let the computer do the calculation a lot?
I'd like to look at it from the other point of view, that you gain something, which is the ability to look at more difficult problems in more sophisticated ways. I think it is a problem. In business calculus, I don't have a problem. But in other kinds of mathematics courses, including the standard calculus course, it is an issue that we have to address. At the moment, we have no idea how much paper and pencil or mental arithmetic or mental manipulations we have to do before it's appropriate to use a computer. And I think that's one of the things we need to work on, and I think it's one of the things we can work on. I think we have to start. It is a problem. Some students are, certainly students are going to know different things if we use a computer to teach them. There are lots of, I could give an extended answer, but I'll quit there.
Paul,
I'd like to second what Wade said, because the issue comes up just as often in talking about teaching statistics. So there's a tradition that students will sit and sum squares in a hot room with a calculator for an hour or two just to prove that they can do it. I've been an advocate for a long time of freeing students of that computation so that they can think about the concepts. As I said earlier, I don't believe that statistics is about numbers. Nobody out in the real world computes statistics by hand. Everybody uses computers to do statistics, and there's nothing wrong at all with students starting off with that and concentrating on the concepts and not on the calculation details.
Great. Thanks for the call, Wade. We have another call from Jessica at USC. Jessica, I don't know who this call is for.
It's for Wade again. You had mentioned Mathematica notebooks, and how can you actually get those?
Well, I think maybe I can pass that around the table, but Addison Wesley is the publisher of those things. I think
they actually exist.
They actually exist.
They actually exist.
And,
Right.
I don't know. It's not
tiny, but it exists.
It's not a product that I'm not sure. Which way am I supposed to go with this?
It's all right.
Okay, we'll go this way. It's not a product that I use. but I think the people that produced it are great. I think it's a terrific product. I'd like to look at it more carefully. It is available from Madison Wesley.
Okay, thank you, Jessica. We have a question from Dave at Montana State. Dave, I don't know who this question is for either.
Well, this is for anybody. Is that all right?
Okay, that's good. We like those.
Okay, here's my question. I'm impressed with the technology, and I'd like to use it, but I have to have a place to shop for data sets. If I have to conjure every potential illustration that I'd like to use, I'm going to have to learn a lot about disciplines that I don't know a lot about. Is there a way for somebody to go shopping for data sets such as the ones that you used in your demonstrations?
That's a good question. I think I'm going to turn that one over to Rob.
Are you a teacher, Dave?
Yeah, I'm a math professor at Montana State, and I'm visiting in NCSA at the moment.
Ah, okay, great. First thing that you do is get a hold of Apple Science CD, which I think NCSA has some copies of. Okay, even though that was produced a couple years ago before we had 32-bit QuickDraw, the data sets are still valid on any machine. NCSA also has some other data there. In addition, there are a variety of data sets available from NASA and from the USGS, I believe. And these are very cheap. Most of these exist on CD-ROMs, but you can also probably send a request into NASA Goddard Space Flight Center at the National Space Science Data Center. It'll take several months to get a data set, but they'll send you a tape, or several years, but they'll send you a tape.
Great.
That'd be real helpful. Just in case we didn't all get that written down, can we write to Apple for any kind of information? Or what?
Dave, we're going to have an 800 number, and with an offer of some additional information on the products that we've talked about. We'll include that information in that 800 number that we're going to talk about in just a minute.
All right, thanks a lot.
Great, thanks for the call. I have a question for you folks, you two in particular, Wade and Paul. Is it difficult to incorporate a computer into the lecture hall? In the laboratory, we've talked about that at great length, but as using it as a projection device, any comments?
It does change the way you teach. You have to replan your lectures, and frankly, I think that's a good thing. Throwing out your lecture notes every now and then and starting again keeps things alive. There are also some issues of technology, of how you're going to do projection. If you have a small room, it's not too hard. If you have a large room, that can get to be a challenge sometimes to be sure you have adequate projection technology. But otherwise, it really enlivens the class. It's something that I often schedule for about 2/3 of the way into the lecture to illustrate things I've talked about, because it wakes everybody up again.
And to wake them up.
It wakes them up
Great.
again.
All right.
But there's another part to that, and that is it takes a little doing for an instructor to figure out how to use that technology. And I think that we need to talk about that a little bit.
Great. Well, gentlemen, I'd like to talk more, but we're out of time here. We hope we've made the most of this hour for you. If you'd like to get some additional information about the projects you've seen today, or tell us what you think about today's broadcast, please call 1-800-733-2753. We do value your comments and hope to hear from you. Our lines will be open on that line until April 8th. Our question and answer phone lines will stay open today for another 30 minutes. That's it for this month's program. Thanks again for being here. Next month, we're going to explore the exciting world of multimedia. We'll take a look at some of the latest developments, as well as the foundations you'll need to create your own project. Join us on April 25th at 1 p.m. Pacific Time with Doug Doyle, who will host Multimedia 201, Beyond the Basics. And thanks again for watching.